Welcome to a session on experimental determination of critical constants. Now, before moving to this topic, I will be discussing the assignment which I had given in the previous session. So, let us move on to that assignment. The assignment was a problem, that is, it goes like that is the van der Waals constants for nitrogen gas are A equals 1.38 atmosphere decimeter raised to 6 mole raised to minus 2 and B equals, this is the van der Waals constant B, is equal to 0.0391 decimeter cube mole inverse. Find the critical constants. What are the critical constants? That is PC, VC and TC. So, these are the critical constants we have to find out, and in the previous session we have seen the relations between them, and using that relation we will be calculating these values. So, the data are written here A is equal to 1.38 atmosphere decimeter raised to 6 mole raised to minus 2 and B is equal to 0.0391 decimeter cube mole inverse. And the relations are, we have Vc is equal to 3b, Pc is equal to a by 27b square and Tc is equal to 8a by 27 rb. Using these relations, we are going to calculate the van der Waals, using van der Waals constant, we are going to calculate the critical constants. Now, we know that Vc is equal to 3b, the value of b is known. So, 3 multiplied by b, that is 0.0391 decimeter cube mole inverse. Okay. So, just multiplying. So, there will not be any change in the unit. You will get the unit as such, that is decimeter cube mole inverse, and by multiplying you will get the answer as 0.1173 decimeter cube mole inverse. So, that is for Vc. Next, let us calculate Pc. This is given by the expression A by 27b square. The value of A is 1.38 atmosphere decimeter raised to 6 and mole raised to minus 2 whole divided by 27 into, that is b square. Remember, do not forget to put the square, that is 0.0391 decimeter cube mole raised to minus 1 whole square. Okay. Now, let us check the units. Here it is atmosphere, in denominator you do not have any atmospheres. Here it is decimeter raised to 6 and here we have decimeter cube twice. So, that again becomes decimeter raised to 6. So, you can cancel this with this. Mole raised to minus 1 square, that mole raised to minus 2. So, you can cancel these two. Okay. And finally, what remains is the atmosphere. Now, using a scientific calculator, you solve the problem 1.38 divided by 27 into 0.0391. The answer will be 33.432 and the only unit left out is atmosphere. So, that will be the answer for Pc. So, we have found out Vc and Pc. Next, we have to find out Tc. Now, before going to Tc, what are the data given are A and B, and in Tc you can see that there is no value of R given here. Now, what we have to do, I have told you, that is check the units given, that is atmosphere decimeter raised to 6, here decimeter cube. So, the value of R should be 0.0821. You can call it as liters or decimeter cube, liter atmospheres per Kelvin per mole. That should be the unit because all A and B are in such units. Okay. Now, moving to the calculation of Tc. See here I have put the value of R 0.0821, A and B, that is the data is given in the problem. R, choosing R should be done with much care so that there will not be much error in our answer. So, substituting, first is 8 into A. A is 1.38 atmosphere, decimeter raised to 6, mole raised to minus 2. Now, denominator whole divided by 27 into R 0.0821 decimeter cube atmospheres per Kelvin per mole. Okay. Next is B into, I will write it below. The value of B is 0.0391 decimeter cube mole inverse. Now, just check. Here we are having decimeter raised to 6. Here we are having decimeter raised to 3. And again here it is decimeter raised to 3, that makes decimeter raised to 6. Get cancelled. Okay. Next is in the denominator we have atmospheres. So, we can cancel this atmosphere with this atmosphere, they get cancelled. Now, here we have mole raised to minus 1 and here one more mole raised to minus 1. Together it makes mole raised to minus 2. So, I can cancel this mole raised to minus 2 with these two. And finally, what remains is K inverse, that is Kelvin inverse. When I take it to the numerator, it becomes Kelvin, and solving, you will get the answer as 127.3754 Kelvin, and that is the value of Tc. So, we have found out all the critical constants, that is Vc, Pc and Tc. So, that is about that assignment. Now, let us move on to our topic, today's topic, that is determination of critical constants, that is the experimental determination. It is not simply finding a relation between them, it is the experimental determination of critical constants, and here we will have two methods. One method is for determination of critical temperature and pressure simultaneously, and there will be another method, that is determination of critical volume. So, there are two methods. One method is for critical temperature and pressure, which we will be determining it simultaneously. The other one is for critical volume. So, Tc and Pc we will find it together, but Vc we will find it out separately. Now, let us move on to the first method, that is determination of critical temperature and pressure. And the method is known by the name Cagniard-de la Touze method. That is the scientist who found out this method. Now, one thing you should remember is, if I take a liquid in an enclosed vessel, I have covered it. Okay. The liquid, it will be here. I have kept it at the room temperature. After some time, some of the liquid gets evaporated and there will be an equilibrium between the liquid and the vapor, that is the vapor of the liquid above it. So, here we will be having the gaseous molecules of that particular liquid, and here we will be having the liquid. So, here it will be in the liquid state and that will be in the gaseous state, and between these two we have a demarcation. That is what we call it as the meniscus. Okay. Or you can say there is a separation between the liquid and the gas. Okay. Because liquid has got a bounding surface, gas does not have a bounding surface, and the meniscus is that of the separation between liquid and the gas. Now let's go to the principle of this method. That is, the Cagniart-de la Touche method principle is that the meniscus, which gives a distinction between the liquid and the gas phase, disappears at critical state. Remember, critical state is a state, okay, at which you can have the liquid, but above that temperature you won't be having liquid state at all. So, critical temperature is when there is the disappearance of the meniscus, and also if we do the reverse case, that is, if I am heating a liquid, the meniscus will disappear, and if I am cooling, that will be the temperature at which the meniscus appears. So, critical temperature is that temperature at which there will be the disappearance of this meniscus, which shows a demarcation between the gas and the liquid. Okay, now let's move on to the apparatus used in it. This is the de la Touche apparatus. Here we have a gas bulb. This is a gas bulb, okay, in which we have taken the substance in the liquid form at room temperature. So, we are going to find out the critical temperature of a substance which exists as a liquid at room temperature. Now, this gas bulb is attached to a manometer. This is a manometer. What is manometer used for? Manometer is used to measure pressure. Okay. So, I am going to use this manometer to read the pressure. Now, once the liquid which is sealed in this gas bulb attains an equilibrium, this liquid will be automatically having a vapor above it. Okay. So, there will be vapor and this is the liquid part. You can clearly see the meniscus. This is the meniscus. Okay. Liquid meniscus. Next, this glass bulb is inserted in an outer jacket, okay, and this outer jacket is filled with either water or any other liquid, where the liquid bath can be maintained at desired temperatures. So, we are having this acts as a water jacket. Okay. A thermometer is inserted in it, thermometer to read the temperatures. Okay, so this is a setup. I will just say it is a sealed bulb in which we have taken a liquid at the room temperature and allowing it to stand for some time. This liquid will be saturated with the vapor above it, okay, and the liquid and the vapor is shown by clearly by a demarcation known as the meniscus of the liquid. Okay. This tube is then attached to a manometer. Manometer, we are using it for measuring the pressure. The whole glass tube, glass vessel is inserted into a jacket where we can use either water or any other liquid to maintain a temperature. You can increase the temperature as well as decrease the temperature. And the temperature of the bath is measured by a thermometer inserted in this jacket. Now, when a temperature is maintained inside the jacket, and that will be the temperature of the liquid and the gas with which it is in equilibrium. Okay. Now, what we have to do is, first we will take the liquid in this. We are going to increase the temperature. The temperature is being increased. What happens is the meniscus goes down, showing that the vapor phase is increasing, that is liquid is getting converted into vapor, and you will get a temperature at which the liquid meniscus disappears. So, we are going to note the temperature as Td, which shows that this is the temperature at which liquid meniscus disappears. Just to show it is a liquid meniscus disappearing, I put it as TD. So now you don't have the liquid meniscus, it's the whole glass vessel is clear, it doesn't have any meniscus. Now it is completely converted into gaseous state. Next step, what I am going to do is, one more point, this is TD and the corresponding pressure is measured from the manometer. Let the pressure be PD, that is pressure at which the liquid meniscus disappears. Next, what I am going to do is, I am going to lower the temperature. Now the whole system, it is in the gaseous state. Now I am going to bring down the temperature slowly, and at a particular temperature you can find the liquid meniscus reappearing. Okay, so that is, the temperature is noted as TA, which shows that the meniscus reappears. Okay, it is appearing. Now the corresponding pressure is measured, let that be PA. This is meniscus appears. Okay, so we are doing both together and we are going to take the mean in order to reduce any experimental error. Okay. Now we will find the critical temperature as TD plus TA whole divided by 2. This gives a mean of these two. That will be the critical temperature. Now pressure PC will be equal to the pressure corresponding to disappearance of the meniscus plus pressure corresponding to appearance of the meniscus divided by 2 in order to avoid any experimental error, and by this way we will be finding out the critical temperature and critical pressure of a particular substance. Okay, so this is the de la Tour's method for determination of critical temperature and pressure, and the principle behind this is, that is, it should be the disappearance of the meniscus, and that will be the same temperature where the meniscus reappears. So that is why during experimental process we are taking the mean of these two. Okay, so critical temperature and critical pressure are measured. Next is determination of critical volume. As you all might be thinking, that is critical volume, it is the volume of 1 mole. Volume of 1 mole of a gas at critical temperature and critical pressure. Okay, so it's very easy. Just keep the substance at critical temperature and pressure and measure the volume of 1 mole of that gas. Will give you the critical volume. But here there is a major difficulty, is that at critical conditions, we know that it is a point at which the total liquid disappears or gets converted into purely gaseous state, and from liquid to gas state means the volume will be very high at critical conditions. It has got a very high volume and it is highly sensitive to small changes in temperature and pressure, or you can say that for small changes in temperature and pressure, the change in volume will be very high. So while measuring the temperature or pressure, small mistakes can lead to large value changes in critical volume. So that's, we don't adopt that method. We have another method to determine the critical volume accurately, and that method is known as Amagat's method. Now Amagat's method is based on a principle known as Cailletet and Mathias' law of rectilinear diameters. That is Cailletet and Mathias' law of rectilinear diameters. What does it say? Now before going to that, I will just clarify some more things. That is, suppose you are having a vessel which contains a liquid and a gas in equilibrium, or you can say that that is the saturated vapor above the liquid. Now, under these conditions, you can see that the liquid will be having a particular density dl, and let the density of the vapor be dV. Now, these densities, that is, the temperature should be constant, you should not change the temperature. At that constant temperature, any liquid which is in equilibrium with the vapor, okay, these two will be having their own densities, and these densities, that is, when the liquid and its vapor are in equilibrium at a definite temperatures, these two densities are known as orthobaric densities. They are known as orthobaric densities. Don't confuse, the temperature should be constant, and that particular temperature, the density of the liquid which is in equilibrium with its vapor, that is very important, and these two densities are known as orthobaric densities, that is, will be the saturated vapor above the liquid. Now, I will go for the law of rectilinear diameters. States that the mean of densities of any substance in states of liquid and saturated vapor. Now, they say that it's a saturated vapor means they are in equilibrium, okay, at the same temperature. That's also very important, which is at the maintained at the same temperature, is a linear function of a temperature, is a linear function of temperature. Okay, here it is again mentioned here, the densities of the liquid and saturated vapor at equilibrium with it are known as orthobaric densities. Now, let us move on to the mathematical expression for Cailletet and Mathias law of rectilinear diameters. That is, it is said that mean of densities of any substance in the liquid state and vapor state. So, here just I have mentioned it, is the density of the liquid plus density of the vapor. You are having two values. So, divided by 2 will give you this factor, that is dl plus dv by 2, means it is an average, or you can use the word mean, or you can say it as average of dl and dV, that is the densities of the liquid and the vapor. So, this value, it is a linear function of temperature, where T stands for the absolute temperature. That is, we know that for a linear equation, we say that y is equal to mx plus c, which shows that it is a straight line. In a similar way, that is dl plus dv by 2 is equal to a plus bt, where t stands for the variable x and this stands for the y. Okay, and this will be the y intercept. Okay, so this is an equation for a straight line, and therefore this shows that it will be a linear function of temperature. Okay, so this is a linear function of temperature. Now, how to find out this? So, this is only the principle. Now, we have to find out the orthobaric densities, and from that, using Cailletet and Mathias law, we have to find out the critical volume. Okay. Now, here what we do is, we will take a small graduated tube. Just to show it is graduated. Okay. Now, in that, I am going to take a particular amount of liquid. So, let this be the liquid meniscus. Okay. And above that, we have a gas. Now, here the liquid taken is with a definite volume. Definite volume. So, volume is known. Okay. Oh, sorry, not volume. Let it be volume also, it's okay. And mass. So, mass is fixed, but volume may change. So, no need to mention it as a definite volume. Okay, you will take a definite mass of a liquid in this graduated tube. Now, what I am going to do is I am going to vary the temperature, and when the temperature is varied, what will happen is that the volume of the liquid and gas varies. For example, if I am increasing the temperature, the volume of the liquid will decrease and volume of vapor will increase. When I lower the temperature, volume of the liquid will increase and volume of gas will decrease. So, what we do is we take a definite mass of a liquid within a sealed graduated tube, and I keep it at a temperature T constant first, and then I will find out the volume of the liquid at that particular temperature and volume of the gas at that particular temperature. Okay. Now, I have taken a definite mass. Okay. Let the mass be m. Let the mass be m. Suppose dl represents density of the liquid and dg represents the density of the gas. This mass can be expressed in the form like volume into density of liquid plus volume of gas into density of gas. You add up this, you will get the mass, because on heating, since it is in a sealed tube, there won't be any change in mass. So, this at this temperature you get one equation like this. Now, at the same temperature, the temperature is maintained constant. Now, what I will do is I will take a different mass, let that be m dash, or I will put it as m1, whatever it is. There is a different mass, the temperature is same. Now, again I am going to do the same process. I am going to keep it in a particular temperature. We do not know what is the density, but we can measure the volume from that. So, I will get VL dash and Vg dash. These are the volumes, but densities will have the same values, that is VL dash into dl plus Vg dash into dg. Because the temperatures are same, there should not be any change in density. So, densities will be constant. Now, this mass we are taking, we know this. We know the volumes of the corresponding liquid and the gas. So, we will be having two simultaneous equations, just like x and y you have. You can solve for dl and dg and find out the corresponding densities of the liquid and the gas at that particular temperature. Now, what I am going to do is I am going to plot it. Now, here you can see that is for a particular temperature, this is a particular temperature at which we have two density values. Here density is greater and here density is less, which means that these are the densities of the liquid and these will be the density of the gases with which it is saturated with. Now, I will mark these two. You do not get the central one. You take this at this particular temperature, I will plot the density here of a gas and liquid here. At another temperature, I will be plotting that of gas here and the liquid here, and you will get a curve like this. Okay. I can extend this curve. See, when extended, it will be like this. So, it is having a flat, you can have a density value that is for this particular temperature, if this is the temperature. For this temperature, you can have density here as well as here. So, you are not sure of what is the density. Now, here is what we are going to apply the rectilinear diameter, that is Cailletet and Mathias law, where it is said that if I take the mean of these two and plot it against temperature, it should be a straight line, right. So, I will take the means, I will take the mean, mark it here and so on. I will extend this line because this is a linear one, it is not a curve, and it is extended, it meets at the point C, and the density value corresponding to the point C will give you the density at critical state. Hope it is clear. That is, we are going to take the means. Since this is a linear function, I can extend it linearly. It cuts on this curve at a point C, and the density corresponding to the point C is taken as critical density. Now, you can find out the critical volume. The critical volume is volume of 1 mole of a gas at Tc and Pc. Okay. So, it is a volume of 1 mole, and therefore, the mass will be molecular mass. Density is, we are going to measure it from this graph, it is experimentally determined, and critical volume Vc is then equal to molar mass divided by critical density. So, mass, here we are having molar mass because we require it for 1 mole. Molar mass divided by critical density will give you the critical volume Vc. Okay. Next is an assignment for the next class. First question is, state Cailletet and Mathias law of rectilinear diameters, which is the principle for the above said method for determining critical volume. And second question is, what is the principle behind Cagniart-de-la-Touche method for determination of critical temperature and pressure? They are measured simultaneously. Now, to conclude, today we have been seeing two methods, that is determination of critical temperature and pressure simultaneously using Cagniart-de-la-Touche method, in which what we will be assuming is that at critical temperature there will be the disappearance of the meniscus, liquid meniscus, and therefore we take the temperatures of appearing the meniscus as well as disappearing the meniscus, and we take the average of both corresponding temperature and pressure, and we will get the values for critical temperature and critical pressure. Next is determination of critical volume, and critical volume, it is very difficult to find the critical volume at critical temperature and pressure, because at that condition small changes in temperature and pressure, makes a wide or great large changes in volumes, and the chances of error are more. And so, we adopt another method to get the exact value for critical volume, and that is the Amagat's method, in which we apply Cailletet and Mathias law of rectilinear diameters. We apply that too, and we will find out critical density, and from critical density, critical volume is found out by dividing molar mass by critical density. So, that is all for today. Thank you.